The problem is really quite simple. Find the best path to get from point A to point B. But now let's make some assumptions. Let's say that point A is on Earth. The Earth is rotating. It's also wobbling on its axis, which means that point A is actually moving like this as it travels through space in its orbit around the Sun. Now let's assume that point B is on the Moon. The Moon is also rotating. The Moon is also wobbling on its axis, which means that point B is describing a motion like this as it travels through space in its orbit around the Sun. Besides this, the Moon is moving around the Earth. So point A and point B do not stay the same distance apart. Also, the Earth and the Moon each have a different strength gravity field. This means that the direction and intensity of gravitational pull will change constantly along our selected path. Because of the movements, the Sun does not always illuminate points A and B. We would like to leave A when it's lit and arrive at B when it's lit. The problem remains the same. Find the best path from point A to point B. But of course, this is a great oversimplification. Soon, man will travel to the Moon. An astronaut will emerge from the four-legged insect-like spacecraft called LEM. He will climb down from it and become the first human being to set foot on the Moon. Then will begin a period of lunar exploration. Others will follow. Missions will become longer and more complex. Other missions will have gone before to develop hardware and procedures. The problems involved in accomplishing these missions are many. Some are obvious, some are not. Just as the hardware must be designed to do the job, so must the mission be designed. The considerations include objectives. What do you want to do? Requirements and constraints. Constraints include hardware performance, the ability of the tracking and communications network, the ability of the astronauts. In order to accomplish the objectives, the spacecraft and crew must be at the right place at the right time. This means the planning of a nominal mission trajectory. But realistically, contingencies may arise which could not be handled by the nominal plan. Alternate trajectories must be designed to handle these possibilities. The design of nominal and contingency missions is the job of the Mission Planning and Analysis Division, MPAD. The accomplishment of this task is governed by the inexorable laws of mathematics. This is Bob Ernle. He is responsible for the compilation of real-time computer requirements for the lunar mission. Without computer facilities, the lunar mission would be impossible. It would take a team of competent mathematicians years to compute by hand just one of the thousands of trajectories that MPAD must compute and evaluate with the computer facilities. But while computers can give you specific answers, it's not possible to educate a computer to make decisions for conducting operations. A man must be in the loop to decide when the computer answer is good enough and when to use it. But where does it begin? Mission planning. For instance, how do you go about planning for a lunar mission?
At least we're satisfying the letter of the requirement. Okay, have you talked with the program office? Are they willing to accept that?
Pete Frank is the chief of the Mission Analysis Branch. He's working on various aspects of the Apollo missions.
That's the best we can do with what we have, meeting all the other mission constraints.
When you first conceive a mission, you must think of objectives versus constraints. For the lunar mission, the biggest constraint is the amount of fuel you can carry. With unlimited fuel, you can choose just about any trajectory you want. But with only a certain amount of fuel that can be carried, you must come up with a realistic way to go. The simplest concept is a direct trajectory. A gigantic spacecraft is launched toward the moon. As it approaches the moon, it turns around, fires its rockets to slow down, and the entire spacecraft lands on the moon. Then everything lifts off and comes back to Earth. This is simple, but expensive in terms of fuel. But there are two other ways, involving rendezvous in Earth orbit or rendezvous in lunar orbit. The one finally settled on was the lunar orbit rendezvous. You launch a spacecraft into Earth orbit, then inject it toward the moon. As you approach the moon, you slow down and go into a lunar orbit. Then you detach a smaller spacecraft and land it on the lunar surface. When your lunar exploration is finished, you launch back into lunar orbit and rendezvous with the orbiting ship. This method is well within our technological capabilities and can fulfill basic mission objectives. But while MPAD does not determine the objectives of missions, it must provide information to those who do.
Plans for modifying radar sites for support of the lunar orbiter are being made. I wonder if you have any comments you'd like to make about which sites would be best to modify first.
Jim McPherson is one of the men who provides this information. He's working on the tracking network for Apollo.
Yeah, there's some reasons for wanting to modify Carnarvon early, though, for telemetry support. Is there a good combination that involves Carnarvon?
Yes, there is a combination. It's not quite as good as the Atlantic stations, and that's Carnarvon, Canberra, and Guam.
Listen, I think we can get some preference expressed about what stations we want modified first, and they'll be accepted. Suppose we write up a memo on this to the director's office and see if we can get something rolling.
I'll get on it right away.
Real good.
The location of the tracking stations must be considered when planning mission tests or experiments that require ground communications, telemetry, or radar tracking. Can mission objectives be supported by the tracking network? Another big area of concern is the placement of recovery forces. Where is the spacecraft going to come down? Where do you put your recovery forces? This is directly dependent upon trajectory design and contingencies. Besides nominal recovery areas, a recovery capability must be available in case of a change in mission plans or an abort. It has been estimated that 90% of mission planning has been in the contingency area. What to do if something goes wrong?
Okay, so the moon is down south then at 28 degrees, and let's say that we've launched on an azimuth of approximately 72 degrees.
Okay, and then put the Earth and Cape Kennedy about so.
Yeah. So then the inclination now to the Earth-Moon plane is not too great.
Given a basic method, lunar orbit rendezvous, given basic design concepts for launch vehicle and spacecraft. The next step is to work out the best trajectory to get to the moon. Hal Beck, head of the Lunar Trajectory Section, is working on this problem.
In some missions, let's take the moon at a 0-degree declination.
For the first lunar mission, a free return trajectory is planned. That is, without mid-course corrections, the spacecraft will leave Earth, go around the moon, and return to a safe re-entry corridor. However, the free return trajectory restricts you to a narrow landing area in a band around the equator. A non-free return trajectory involving different transit times will allow landings in a much greater range of latitudes. These will be used for later advanced missions. There's a number of trajectories, each of which has advantages and disadvantages. Once you've chosen the one you want, you fit the rest of the mission to it.
It's a two-burn problem, and at the end of the first burn, you have to constrain the apergy of your lips. This is a practical constraint. It's just to keep it a certain altitude above the earth.
So this is some new theory you've had to develop?
You might mention that this is the...
Jim Dalby is chief of the mathematical physics branch of MPAD. One of his jobs is to develop mathematical programs for mission planning, programs that give optimum trajectories for maximum results.
So this is a mathematical innovation to take care of a practical mission planning problem.
Yes, although the parity constraint he's talking about has been developed for some time, but we've had to develop the accuracy of the second variation program.
I see.
To handle
this parity constraint is an intermediate constraint, as an example.
Yeah, right.
Right.
I got you.
The equation I already have on the board is a basic equation and calculus variations, and if you take the first variation of it and set it to 0, this is a necessary condition for a extremal, and it's the basis of deriving all our conditions that we need. Jerry is having this problem for us, and I'd like for her to get up and discuss.
Spaceflight is a unique business. Unique mathematical methods must be worked out to handle it, and old techniques are developed for new applications. These techniques can solve extremely difficult problems in a very short time. A 6-hour problem, for instance, can be solved in 20 minutes. New applications appear every day. Other methods are tailor-made to fit individual needs. For example, predicting accurately where the spacecraft is, how fast it's going, where it's going to be. What can the tracking network do, and how accurate will the answers computed from tracking data be? And this must be done long before the mission is flown. There is a residual uncertainty in all measurements. This uncertainty must be stripped away mathematically and the best estimate figured out. Then the measure of confidence in these estimates must be determined. Once the formulation and logic is underway, the computers come in.
That one was about 30,000 right there. Yeah, about 30,000. Gets out quite a bit for this.
One of these computers is the hybrid, consisting of digital and analog computers tied together to act as a single unit.
Work cases, we're doing the last two here, and we thought we'd show the effect here with wind and without it.
This computer is used for abort studies, dispersion analyses, designing displays for flight controllers. A versatile computer requiring versatile people to operate it and program for it.
We'll put it in the wheel? Yeah, we'll see how the effect of the wind is.
The lunar rotations are going to take our move of the site, right?
Right.
Mission design affects everyone working on a mission.
So if we want to pass over the site one orbit later, the CSM is going to have to pass to the south of the site.
The design of the hardware must be taken into consideration. Jim Taylor's main concern is the assessment of landing areas on the moon.
The orbit plane on the site you want to go. If we make a plane change at 90 degrees from the site, 2-degree maximum, what's the delta be?
180 feet per second.
That's
As mission planning gets farther down the line, data are given to the builders of the systems. And the systems are always changing. For instance, the lunar module. Early plans for the lunar rendezvous called for the LEM to be active with a fairly inert command module. However, the LEM is getting heavier and more fuel critical. Therefore, since the command module has plenty of fuel, it will go to meet the LEM.
You know, one of the things on the lunar mission is that there is no logic for the time that the burn initiates. So, but if you follow the logic of all the other missions, what we build in is a prediction, or like it was occurring on 278, there is a built-in prediction of the elapsed time to the burn, based on some calibration. If you know the burn arc's going to be so long.
Operational planning, the way to do things, is now entering the picture. Morris Jenkins is responsible for the compilation of program requirements for the Apollo onboard computers.
Time should start, when it should occur.
Well, if you know where your perigee is, and you're intending to circularize at the same altitude as your perigee, you should be able to ignite on them.
Since the onboard computer will be used by the lunar astronauts to solve essential navigation problems, the program must be framed to fit their needs as closely as possible. The astronauts should have a pretty good idea of what the answers will be before the computer spits them out. From this operational planning comes the reference trajectory. This is one of many documents assembled by MPAD. Because of the innumerable factors involved in mission planning, it is important that math aides bring these documents out on time and in usable form. Ed Lineberry, chief of the Rendezvous Analysis Branch, is largely responsible for the work leading to our first space rendezvous, a technique vital to the success of the lunar mission.
Did Ken talk to you about the corrections we want to make on this particular?
Yes, sir.
All we'll have to do is go back and change the scale, and just make it velocity in feet per second. I think other than that, it looks real good. You think you can have it completed by 3:30?
Yes, sir, I believe so.
Okay.
The compilation of documents containing mission information is critical. This information must be available to the people who need it, when they need it, if mission schedules are to be met.
That's a ground track, and of course we fixed it that way so we get coverage from all the...
Design of a specific mission begins about 1 year before launch. Often, a flight will change a few months before launch because of changes in mission objectives, rules, or hardware capabilities.
Down about there.
Planning must be flexible to handle this.
After the first SPS burn, and
Where's the update?
after the first SPS burn, we pitched down in order to keep communication.
Carl Huss, chief of the Flight Analysis Branch, produces detailed trajectories for specific missions.
Until we get around, until that attitude corresponds to the inertial attitude of the second burn. What we do is, of course, go through the launch phase, and then we stay on the booster for 10 seconds after cutoff, after the booster cutoff, that is. That's to allow for tail off and for Marshall to get their data. Then we RCS for 11 seconds. We go through the separation sequence.
Designing for a specific flight means working with actual details of the systems rather than with somebody's estimate. How much does the spacecraft weigh? How much thrust is available from the main propulsion system? When do you thrust? How long? What attitude must you have? And planning for the nominal mission is just part of the responsibility. Is contingency planning and operational procedures that go along with emergency and what-if situations. "90% of specific mission planning is on the emergency or abort problem, and 10% on the nominal mission. This means a lot of the work is never used, and the hope is that it never will be. While you try to think of everything, many things don't come up until the simulations start, 2 or 3 months before launch. The astronauts fly rehearsal missions from the mission simulator. Flight controllers are at their consoles just as they will be for the real mission. And flight controllers can be pretty fiendish in coming up with things you haven't thought about. They need answers. And others need answers. Recovery forces. Tracking stations, range safety, can launch, you have to know where the spent launch vehicle is going to land, to be sure it doesn't end up in downtown Miami. Once the mission is ready to go, the launch vehicle on the pad, the crew in place, much of the work of MPAD is done, but not all. The astronauts in the spacecraft need to transmit and receive information. They do this through the tracking stations of the Manned Space Flight Network, to the Mission Control Center in Houston. When a flight controller in the Mission Operations Control Room calls for information, he needs it immediately, whether it's on the big display board, a data TV channel, or an indicator light. If an astronaut is going into orbit around the moon in 5 minutes, and the information he needs doesn't reach him for 6 minutes, it's not going to do him much good. This real-time information comes to the flight controller from the real-time computer complex located on the first floor of the Mission Control Center.
MOC? No. You can put your sign key down. Go. SCA's computer suit.
I see clock's running.
Right.
MOC 16 hours, 31 minutes.
Right. Dynamics run into
The operation of this complex during a mission is a vital function of MPAD. Here, data obtained from mission analysis are stored. For a Gemini rendezvous mission, the efforts of over 200 programmers for a year and a half are required. The real-time program consists of about 650,000 separate instructions. For the lunar mission, this will be at least doubled. One of the men supervising this complex during the mission is Jim Walker.
Roger. Okay, I'm through with him then. MOC dynamics. Plot tape mounted. There's a plot tape mounted.
Dynamics, computer suit.
You can read it. Go ahead.
I don't think we want to go through the PO data sheet.
You got your targeting ground suit.
Right. SCA's computer suit.
Go computer suit.
We have GMTLO of 163908.
Right, I see that.
Information is relayed to astronauts, recovery forces, launch personnel, experimenters, everyone concerned with the flight phase of the mission. Computers tell flight controllers what can be done, but first men must tell the computers. And this is just part of the job.
Why don't we go ahead with 08? 59 Stony, stand by for a 10-second count to engine ignition. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition. Lift off. Clock is running.
We got a lift
In a staff support room adjacent to the Mission Operations Control Room, mission analysis experts constantly analyze data and advise flight controllers. They stand ready to handle any occurrence during a mission.
That's a hydraulic switchover.
164233.
Dynamics. 164233. Roger. That's plenty of time to correct. Retro.
Did you call me retro? This is trajectory.
Beginning to pitch down.
We got something going
Raj,
here.
164233.
Raj, I understand.
To give mission planners another set of tools during a mission, the auxiliary control room serves as a supplement to the real-time computers. These are high-speed computers that can handle any number of problems. The man responsible for the management, development, and manning of this complex is Clay Hicks.
ACR trajectory.
Go ahead.
Would you run the heat processor for a 200 by 218 orbit?
Raj.
And also, can you give me a time estimate on that request?
Raj, it'll take approximately 15 to 20 minutes.
Okay, rush it up and I'll be standing by.
Right.
Sometimes things come up for a mission not foreseen in real time. Something has always happened during every mission ever flown that's never been thought possible. These things flow into the auxiliary computer room, where you can improvise in real time.
Could you get this case and get it real quick for us? Trajectory ACR. Larry's gone out.
Even after the mission is down, the work of MPAD goes on. The mission is studied in detail during post-flight analysis. Don Inserto is head of the post-flight trajectory analysis section. He works with all the other sections of MPAD to find the actual mission trajectory and compare it with the nominal. Where they don't match, the reason must be found. They locate errors. For instance, from post-flight analysis, it was learned that the Hawaii tracking station was located several hundred feet from where it was originally thought to be.
We don't really know.
You know how it started.
Well, all right, but nobody's talking about changing anything, are they, at this point?
Not that I'm aware of.
Well, then...
Not as far as we're concerned. Well, I got this phone call, John.
It's a complex job involving computers and the work of thousands of people.
That's right. I mean, as far as we're concerned, everything's still the same.
Not being able to hit the entry quarter never came into the picture as far as I knew.
But telling Chris-craft that kind of stuff is like
blowing
the whole world up. You don't do it.
So you're not in trouble there as far as your guidance and your dispersion of SPS.
Well, you're not inseparable. Apparently, you've only got a 0.15 corridor because you're trying to meet some heating requirements.
No, the 0.5 degree is that the answer you get from your dispersions?
No, you might also mention now that
0.5 was, or that was their accuracy they wanted originally. 0.5.
That was the oldest.
That was.
So what are the dispersions give you?
As chief of the Mission Planning and Analysis Division, John Mayer is well aware of the complexity.
Okay, well, what are the dispersions now? What's the answer you get? I'll bet it's 0.5.
The first lunar mission will be the beginning. Later missions will stay for longer periods on the moon and continue its exploration. But getting to the moon is like getting to first base. From there, we'll go on to open up the solar system and start in the direction of exploring the planets. This is the long-range goal. It's a learning process. As more knowledge is gained, more confidence is gained. More versatile hardware can be built. Simpler ways of doing things will be found. The flight crews will do more and more. As usual, 90% of the job of MPAD will be trying to figure out what can go wrong and what to do about it. And without computers, it couldn't be done. These complex arrangements of glass, metal, insulators, and electronics, conceived and built by man to aid him on his quest for knowledge. Man cannot match the speed of computers. Computers cannot match the creativity of man. For with all the awesome speed of computers, the mind of man remains the activating factor. To leave A when it's lit and arrive at B when it's lit. The problem remains the same. Find the best path from point A to point B. But of course, this is a great oversimplification. Also wobbling on its axis, which means that point B is describing a motion like this as it travels through space in its orbit around the sun. Besides this, the moon is moving around the Earth. So point A and point B do not stay the same distance apart. Also, the Earth and the moon each have a different strength gravity field. This means that the direction and intensity of gravitational pull will change constantly along our selected path. Because of the movements, the sun does not always illuminate points A and B. others will follow. Missions will become longer and more complex. Other missions will have gone before to develop hardware and procedures. The problems involved in accomplishing these missions are many. Some are obvious, some are not. Just as the hardware must be designed to do the job, so must the mission be designed. The considerations include objectives. What do you want to do? Requirements and constraints. Soon, man will travel to the moon. An astronaut will emerge from the four-legged insect-like spacecraft called LEM. He will climb down from it and become the first human being to set foot on the moon. Then will begin a period of lunar exploration. The problem is really quite simple. Find the best path to get from point A to point B. But now let's make some assumptions. Let's say that point A is on Earth. The Earth is rotating. It's also wobbling on its axis, which means that point A is actually moving like this as it travels through space in its orbit around the Sun. Now let's assume that point B is on the Moon. The Moon is also rotating. The Moon is also